Hi everyone, in this tutorial I will show you how to estimate remainder terms. Let's look at an arbitrary sum. Let's say we have a sum like this, summation from 1 to infinity a sub n. We want to separate the first few terms of this sum. Let's say I have the first 3 terms. I separate the first 3 terms. Then I have left some more terms, right? And I can write those remaining terms by using signal notation, right? In signal notation, this remaining part will start from 4, will go up to infinity of the same a sub n term, right? So here I have the first 3 terms, and I have the remainder. This part is called the remainder term, and this part is called the first 3 terms, right? And if I do this for an arbitrary number of terms, not just 3, but just an arbitrary number of terms, let's say k terms, this is how it looks. Summation from 1 to infinity, a sub n. Let's separate the first k terms, then I have a1 plus a2 up to a sub k, right? These are the first k terms, and usually you can find the sum of these first k terms by using a calculator. And you have some more terms left, and I can write all those terms left in the following signal notation. Summation starts from k plus 1 up to infinity a sub n. Okay, so this is the remainder when I separate the first k terms. Next, we will see how we can estimate this remainder term by using improper integrals. So I want to put something bigger than this sum, which will be an improper integral. Okay. The way to estimate that remainder term is actually nothing surprising to you guys, because we used similar kind of idea earlier when we talked about the integral test. For example, let's look at the following sum. Summation from 2 to infinity 1 over n squared. And probably you guys remember this series converges either by P series test, or if you remember the original idea, it was the integral test. We said this sum is similar to the following improper integral from 2 to infinity 1 over x squared dx. And we know that this improper integral converges, so does the infinite sum. The series converges. Alright, so now we will be a little bit more precise, and we will use this kind of an improper integral to estimate something like this. So this is best understood on a picture. So let's look at the graph of 1 over x squared, and let's try to visualize this sum and this improper integral or some other improper integral on this picture. So let's say here is point 1, here is point 2, here is point 3, and so on. And remember the Riemann summation, I will go ahead and build rectangles on the top of these intervals. So this will be my first rectangle, this will be my second. Let's take 4 here, and let's build another rectangle. Let's take another point 5, and let's look at the following rectangle. Here I already have 1, 2, 3, 4 rectangles, right? And I can compute the area of these rectangles separately. For example, let's look at the area of first rectangle. What's the area of the first rectangle? What's the base? Base is just 1. What about the height? Height is value of this function at 2. So it is nothing but 1 over 2 squared, right? What about the area of the second rectangle? It will be 1 over 3 squared. What about the area of the third rectangle? It will be 1 over 4 square, and so on. So as you can imagine, I can find the area of all these rectangles here. Let's look at the sum of all those areas of all those rectangles. So sum of areas of rectangles will be what? When I do this splitting at integer points and when I build rectangles on the top of those sub-intervals, I get infinitely many areas, and the sum will be area of the first rectangle 1/2 square, area of the second one 1/3 square, the next one will be 1/4 square, and so on. And as you can see, this is nothing but the series I wrote up here, right? So this area is nothing but summation from 2 to infinity 1/n square. Alright? So let's try to find something bigger than this sum, or something bigger than sum of areas of all those rectangles. Let's go back to the picture and let's try to play with it a little bit. Let's go ahead and look at let's look at the following area. In addition to rectangles, let's add these extra pieces too. Then what do I get? When I look at these extra pieces and the rectangles, I get this bigger area. This bigger area is what? This bigger area is the area underneath the curve, right? And I can write this new shaded area as an improper integral, right? The area of this red shaded region will be improper integral from 1 to infinity. Here this 1 is important, that's the starting point, 1/x squared dx, right? And as you see on the picture, sum of areas of rectangles is smaller than the area of this red shaded region. So I get the following inequality. We get the following inequality. Summation n from 2 to infinity 1/n squared is smaller than integral from 1 to infinity 1/x squared dx. Now this is a correct inequality, and the good news is I can compute this improper integral. Remember, this is nothing but limit as n goes to infinity, integral from 1 to n 1/x squared dx. And when you compute this proper integral and take the limit, you will see this sum will be 1. Sorry, this integral will be 1. So what I know the following. This sum here, even though I don't know the value of this sum, I know this is less than 1, right? So this will be the key idea in the problems, in the related problems, and we will use an improper like this to estimate the remainder term. Remember earlier when we talked about the general setup, we said we have a sum like this, summation from 1 to infinity a sub n, and when we separate the first k terms, namely the sum from a1 up to a sub k, then the remainder was summation from k plus 1 to infinity a sub n, right? And in the problems we will be interested in estimating this remainder term. And here, as you see in this example, we can estimate the remainder term by using improper integrals. Namely, if we have a remainder term like this, summation from k plus 1 to infinity a sub n, this is always smaller than integral from k to infinity f of x dx, where f is the function that gives me these terms a sub n's, and the important thing here is the sum starts from k plus 1, but the improper integral starts from k. So I have to take a step back to get something bigger. Okay? Next, let's look at the following problem from WebAssign. Here we have a summation from 1 to infinity up to n squared. Here we have a sum. Summation from 1 to infinity 1/n cubed. in part A, we want to look at the sum of the first 10 terms to estimate the given infinite sum. So let's look at this sum and let's write out the first 10 terms. What will be the first term? The first term is 1. What about the second one? 1 over 2 cubed, which is 1 over 8. What about the next term? 1 over 27, right? Plus 1 over 4 cubed, which is 64, and so on. So when I separate the first 10 terms, the 10th term will be 1 over 10 cubed, right? Which is 1 over 1000. This sum has some more terms, namely summation from all the remaining terms will start from 11 up to infinity, still 1 over n cubed, right? So now I have how many terms here? I have 10 terms here. Can I use a calculator to find the sum of these 10 terms? Yes. So let's go ahead and use a calculator to calculate the sum of these 10 terms, and let's put our answer here. I will not do this calculation, but once you do this calculation, you will get a number that you will put in here. Okay? So that's part A. What about part B? Let's look at part B. In part B, I'm looking for a value of n that will do what? That will do the following. When I replace the original sum s by s sub n, the summation up to the nth term, I want the error to be less than this number. Remember, if I separate the first n terms, what will be the remainder? When we separate the first n terms in a sum, the remainder term will be summation, let's this time call it k, from n plus 1 up to infinity, a sub k, right? If I separate the first n terms, this will be the remainder. In this problem, I wanted to keep this remainder less than 1 over 1000, right? That was the problem. Here, let's remember the sum. The summation we were interested in was summation from n plus 1 up to infinity, 1 over n cubed, right? And I want to make this thing from less than 1 over 1000. It is very difficult to evaluate this sum, as you see right here. Alright, we will go ahead and take this sum, summation from 1 to infinity, 1 over n cubed. We will go ahead and separate first few terms, namely in this problem we want to separate n terms. Here, don't get confused with this n and this indexing set n, so that's why I will go ahead and change the problem, this sum, into the following. Summation from k equals 1 to infinity, 1 over n, 1 over k cubed. So here I will go ahead and separate the first n terms, which is like 1 plus 1 over 8 plus up to 1 over n cubed, right? This is the sum of first n terms. In this case, what will be the remainder? The remainder will be summation k equals n plus 1 up to infinity, 1 over k cubed, right? And in this problem, we want to keep this remainder term less than 1 over 1000, right? Okay, it is kind of difficult to find this sum, so what I will do, I will use that improper integral estimate we discussed earlier, namely this sum, k from n plus 1 up to infinity, 1 over k cubed. I know this is smaller than the following improper integral. Improper integral from n to infinity, 1 over x cubed dx, right? So, if I can keep this integral by choosing a correct value of n, if I can keep this improper integral less than 1 over 1000, then that means I can also keep this remainder term less than 1 over 1000. So that means if I want to keep this sum small, this remainder term small, I have to keep this integral small. Okay, so I have to choose the smallest value of n such that this improper integral is less than 1 over 1000. So let me write one more time what we are looking for. We are looking for a value of n such that integral from n to infinity 1 over x cubed dx is less than 1 over 1000. So what should I do? I should go ahead and compute this improper integral. Improper integral from n to infinity 1 over x cubed dx. This is not such a difficult improper integral. This is limit as n goes to infinity. Integral from n to n 1 over x cubed dx. And when you take the integral and compute the limit, you will see the following. Integral of 1 over x cubed is 1 over negative 1 over 2x squared. So this integral will turn out to be 1 over 2n squared. Okay, so that's the improper integral. And remember, I want to keep this improper integral less than 1 over 1000, right? So that means I want to choose n such that this inequality is true. So let's rewrite this integral. Let's rewrite this inequality. Let's do cross multiplication. Let's take 1000 there and 2n squared there. That gives me 1000 has to be smaller than 2n squared, which means 500 should be smaller than n squared, right? So here, that means I have to choose n such that n squared should be more than 500. So for example, if I choose n 10, that will not work, right? Because 10 squared is 100, and 100 is not bigger than 500. What about 20? If I choose n equals 20, then 20 squared will be 400, and 400 is not bigger than 500. What about 30? Then here I will get 30 squared. 30 squared is 900, and 900 is indeed bigger than 500. But here the problem is this: when I choose n equals 30, I get this inequality, but maybe a smaller value of n would work. For example, 29 will work as well, right? 29 squared will be more than 500. So it is our goal to choose the smallest n that will give me this inequality. So it will be something definitely bigger than 20 and probably something less than 29. And when you play with it, you will see the following. N has to be bigger than square root of 500. So if you look at the decimal value of 500, and if you make it a little bit bigger, you can find the correct integer value for n. And I think it turns out to be 23. We'll just do that. So 23 square will be more than 500, but 22 square will be smaller than 500. So I have to choose n as 23. What's the meaning of this? The meaning of this is the following. So for n equals 23, when I look at the following sum, summation from 1 to infinity, 1 over k cubed, and I separate the first 23 terms. So it's like 1 plus 1 over 8 plus 1 over 27, 1 over 64, up to 1 over 23 cubed. I will get the remainder term, summation k from 24 up to infinity, 1 over k cubed. What I know, this error term, this remainder term, is smaller than 1 over 1000. And I can use a calculator to compute this sum here. After all, I have only 23 terms here, and I can use a calculator to compute this sum here, right? So if I want to find the exact value of this sum, it will take some time, but if I'm fine with error that is smaller than 1 over 1000, then I can go and just compute the sum of first 23 terms, and that will give me a very good approximate value. That approximation will be the error will be smaller than 1 over 1000, which is a quite big number. Alright? Let's look at the next problem from Redasign. Here we have another sum, summation from 1 to infinity 2 over n cubed. And I want to find the correct truncation that will give me error up to 3 decimal places. So which means the following. So here I have this sum. Let's say I separate the first k terms, which will be like 2 over 1 to the 5th, which is 2, plus 2 over 2 to the 5th, which is 2 over 32, which is 1 over 64, plus 2 over 3 to the 5th, which is 273, and so on. So let's say I go and take the values up to k, so I will get 2 over k to the 5th. These are the first k terms. And then I will have the remainder. The remainder will start from k plus 1, will go up to infinity, and I will have 2 over n to the 5th. And my goal is to keep this error less than 3 decimal places, which means I want to keep this error less than 1 over, again, 1000. Okay, how do we find the value of k? How many terms do we have to separate? Again, we will use improper. So my goal is to make this sum, summation from k plus 1 to infinity, 2 over n to the 5th, less than 1 over 1000, right? That's my goal. I want to find the value of k. K is the value I'm looking for, such that this sum is less than 1 over 1000. But remember, we know that this sum here is smaller than integral from k to infinity 2 over x to the 5th dx, right? This improper integral is bigger than this sum. So if I can make this improper integral less than 1 over 1000, then I accomplish what I wanted at the beginning. And the good news is I can compute this integral. Again, this is limit as n goes to infinity, integral from k to n, 2 over x to the 5th dx. And when you take this integral and take the limit, we will get the following. Integral of 2 over x to the 5th is negative 1 over 2 times x to the power 4. 1 over, so one more time, negative 1 over 2 times x to the power 4. So when you plug in k and n and take limit as n goes to infinity, you will get the following expression. This integral is 1 over 2k to the power 4. Okay? So I know what this integral is, and remember I wanted to keep this less than 1 over 1000, right? So that means I want to keep, when I do again cross multiplication, I get 1000 over 2 has to be smaller than k to the 5th, which means 500 has to be smaller than k to the 5th. So I'm looking for a number, k, the smallest value of k, such that the 4th power is more than 500. So for example, let's take k equals 2. 2 to the power of 4 is 16. So this definitely doesn't work, right? What about k equals 3? 3 to the power of 4 is 81. This will not work either. What about k equals 100? That will definitely work because 100 to the 4th power is way bigger than 500. But it's like in the previous problem, this is a very big number. I want the smallest such k. So when we do a little bit algebra, we see the smallest value of k that gives me this inequality will be, smallest value of k will be 5. So when I separate the first 5 terms, then the error will be smaller than 1/1000. In other words, in 3 decimal places. So let's go back and find the sum of the first 5 terms. So let me summarize it one more time. We were interested in the following sum: summation from 1 to infinity, 1 over n to the 5th. Sorry, I think it was 2 over n to the 5th. And I wanted to find an approximate value that's in 3 decimal places. And we notice that if we separate the first 5 terms, then the remaining term will be summation from 6 to infinity, 2 over n to the 5th. And we notice that here this remainder term is smaller than improper integral from 5 to infinity, 2 over x to the 5th dx, and we notice that this improper integral is smaller than 1/1000. So that means if I want to find an approximate value of this sum within 3 decimal places, it is enough to look at the sum of these 5 terms. But what are the first 5 terms? Let's write them out. The first term is 2 over 1 to the 5th is just 2. The second one is 2 over 2 to the 5th. Then I have 2 over 3 to the 5th. Then I have 2 over 4 to the 5th. And I have plus 2 over 5 to the 5th, right? So here I have the first 5 terms. And again, I can use a calculator to find the sum of these. I can use a calculator to find the sum of these first 5 terms, and that will be my approximate value within 3 decimal places. Finally, let's look at the following problem. Problem number 11. We want to use the first 10 terms to approximate the following sum. So here, again, I can go ahead and write the first 10 terms. The first term will be sine square 11 times 1, which is 11 over 1 square. And the next term will be sine square 11 times 2, which is 22 divided by 2 square, which is 4, and so on. So I can write out the first 10 terms. The 10th one will be sine square 110 divided by 10 square, which is 100, plus I will have the remainder. Remainder term will start from 11, will go up to infinity, sine square over 11n divided by n square, right? So this is the remainder term. And this initial segment is the sum of the first 10 terms. Again, I can use a calculator to compute the sum of these first 10 terms, and I can put that here. That takes care of the first part. In the second part, I want to find an upper bound for the error. So where is the error? Error is this remainder term, and I want to approximate to this remainder, this error term. So let me write that down one more time. This is the term we want to estimate, summation from 11 to infinity, sine square 11n divided by n squared, right? And again, I will go ahead and approximate this sum by an improper integral. Improper integral from 10 to infinity, sine square 11x divided by x squared dx. And here, as you can see, this is not such an easy integral to take. So instead of taking this improper integral, I will go ahead and do one more estimate. And that estimate will be the following. I will keep the integration interval as it is. Here I will write something bigger. I will keep the denominator same. Here at the numerator I have sine squared 11x. What's the largest possible value for sine? Sine can be at most 1, so sine square will be at most 1 too. So I get 1 over x squared dx, right? Okay, so this improper integral is easy to take, and also it is bigger than this remainder term, this error term I have at the beginning. So let's go ahead and compute this improper integral. We have done many of them already. This is limit as n goes to infinity, integral from 10 to n, 1 over x squared dx. And once you take the integral and compute the limit, you will see this improper integral is exactly 1 over 10. So the error we had at the beginning is smaller than the value of this improper integral, which is 1 over 10. Right? Next, let's look at the remainder for alternating series. This time we have a series of the following form: summation from 1 to infinity, negative 1 to power n, a sub n. This is an alternating series. And again, like in the previous case, let's say we go ahead and separate the first k terms. Then we will have the following remainder: summation starting from k plus 1 up to infinity, negative 1 to power k, so negative 1 to power n, a sub n, right? So this part is, again, this is the same remainder term. In the previous discussion, when we had no negative 1 to power n factor and we had only a sub n, we estimated this remainder term by using an improper integral. When we have an alternating series, then this discussion is much easier. We don't need to use any improper integrals. We know the following fact: this remainder from summation from k plus 1 up to infinity, negative 1 to power n, a sub n, in absolute value, this error term in absolute value will be as much as a sub k plus 1. In other words, the very first term in this alternating sum is the largest possible value for that remainder piece. Okay? So that's quite important, and we will make use of this in the next two problems. And as you can see, I don't have to take any improper integrals or anything like that. Let's look at the following problem. We have an alternating sum, negative 1 to power n divided by 3 to the power n times n factorial. And I want to approximate this sum correct to 4 decimal places. So again, our trick is I will go ahead and separate the first k terms, and I can find the sum of these first k terms by using a calculator. Then I can put that number in here. But the question is, how many terms do I need? How many terms I have to pull out to get something correct to 4 decimal places? Which means I want to make this remainder, which is summation from k plus 1 up to infinity of negative 1 to power n divided by 3 to the power n times n factorial. I want to keep this remainder term less than 1 over 10 to the power 4, right? That's our goal. I want to keep the error of this remainder less than this value. Here we have an alternating series, and we know how to estimate alternating series. So let's remember that. Let me write down the remainder one more time. Summation from k plus 1 up to infinity, negative 1 to power n divided by 3 to the power n factorial. We know that in absolute value, this remainder is smaller than the very first element in this sum, right? So what's the very first element? I will forget about the negative 1 term because everything in the absolute value. The next term will be 1 over 3 to the power k plus 1 times k plus 1 factorial. And I want to keep this expression less than 1 over 10 to the power 4. Now let's do cross multiplication. That means I want to keep 10 to the power 4 less than 3 to the power k plus 1 times k plus 1 factorial. So again, the goal is to choose the smallest such k such that this inequality holds. For example, k equals 2 will not work because when I plug in k equals 2, I get here 3 to the power 2 plus 1, which is 27, times 2 plus 1 factorial, which is 6. 27 times 6 is not bigger than 10 to the power 4. At the same time, if I choose something very big like k equals 100, then definitely 3 to the power 101 times 101 factorial will be bigger than 10 to the power 4. So it is my goal to find the smallest such k where this inequality holds. So now we have to do a little bit trial and error, and we will find this number. So once you play with it a little bit, go ahead and plug in some numbers. Let's say plug in 5, 4, 6, 7. Then you will see this. You will find the smallest value of k such that this expression is greater than 10 to the power 4. When you go ahead and do the calculations in the previous slide, you will see that k equals 4 will work. Namely, if I separate the first 4 terms here, then the remainder will be correct to 4 decimal places. Sorry, the remainder will be smaller than 1 over 10 to the power 4. So let's look at the first 4 terms here. The first one is negative 1 over 3 to the power 1 times 1 factorial, which is negative 1/4. The second one is plus 1 over 3 to the power 2, which is 9, times 2 factorial, which is 2, which is 18. And I have minus 1 over 3 to the power 3, which is 27, times 3 factorial, which is 6. 6 times 27 will be 162. And I will have the fourth term plus 1 over 3 to the power 4 is 81, times 4 factorial. 4 factorial is 24, so I will get here 1 over 81 times 24. And I will have the remainder, right? And we notice that this remainder term is smaller than 1 over 10 to the power 4, which means if I look at the sum of these 4 terms, I will get something correct to 4 decimal places. So I can use my calculator to compute the sum of these 4 terms, and I can put that right here. That will be the answer. Next, let's look at the following problem from river sign. Again, we have an alternating series, negative 1 to the power n plus 1 divided by 6 times n to the power 4. You can use the alternating series test to see that this series converges. In the next part, we want to find how many terms we need to add, we need to separate in order to find the sum with the following indicated error. Okay, so let's say I go ahead and separate the first k terms. So I will go ahead and write out the first k terms, and what will be the remainder? The remainder will be summation starting from k plus 1 up to infinity, negative 1 to the power n plus 1 divided by 6 times n to the power 4. And our goal is to keep this error in absolute value smaller than 0.00005, which is 5 over 10 to the power 5, which is also nothing but 1 over 2 times 10 to the power 4. So my goal is to keep this error less than 1 over 2 times 10 to the power 4. Let me write the error term one more time. My goal is to keep this summation from k plus 1 up to infinity, negative 1 to the power n plus 1 divided by 6 times n to the power 4, smaller than 1 over 2 times 10 to the power 4. Okay, in absolute value, I want to keep this remainder less than that value. And remember, when we talked about the remainder for alternating series, I know that this alternating sum here is smaller than the value of the first element. So what will be the first entry? Forget about the negative 1 part. The first entry will be 1 over 6 times k plus 1 to the power 4. So it's my goal to keep this expression less than 2 times 10 to the power 4. And again, when we do cross multiplication, we see that we want to keep 10 to the power of 4 divided by 3 less than k plus 1 to the power of 4. If you want, we can take the 4 powers of both sides, so we get 10 divided by 3 to the power 1 over 4 has to be smaller than k plus 1. So my goal is to choose the smallest such k. And again, you can use a calculator to approximate this value. When you use your calculator, you will see this number will be roughly 7.5. So in order to establish this inequality, I have to choose k at least 7, right? So for k equals 7, I will get this inequality satisfied, which means the error will be smaller than the demanded threshold. So when I go back and use this value, I can get the correct approximation. So the answer will be, I need to use at least 7 terms to get an approximation with error at most